Let's start with this problem and give it a shot. Don't just listen for me to explain how to do it, but hit pause, try and work it out, and then check and see if you did it correctly. So we have 2 points. The point A is 1, -6, and the point B is -3, -4. We want to write the component form of a vector. So first of all, the component form of a vector we write like this, 2 numbers separated by a comma, or we can write it vertically with 2 numbers there. We want to write the component form of a vector. It's going to be in the same direction as vector BA, but with a magnitude of 1. So first of all, let's go ahead and try and come up with vector BA. So from B to A, remember we do terminal minus initial. So we're going to get BA in component form to equal +4, 1 minus a -3, and then -6 minus a -4 is -2. Another way to think about it is look at the coordinates of B. So if I'm starting at B and I'm at -3 and I go to 1 in the x direction, that's moving 4 to the right, that's positive. And then if I'm at -4 and I'm moving to -6, that's moving left 2, so that's -2. All right, let's get rid of all this extra stuff here. Okay, so obviously this has a magnitude. I'm going to write the vector the other way, 4, -2. The magnitude of this vector is going to equal the square root of 20, or 2√5. And so we want it to have a magnitude of 1, so what are we going to do with that? Well, what we need to do is we need to shrink this vector down, but we're not going to change its direction. So let me draw the vector 4, -2. There's our vector right there. So what I'd like to do is I want to shrink this thing down so that it only has a length of 1. Well, how can I do that? Well, we learned that if we multiplied a vector by 2, by a scalar, let's say 2, it would double in size. So now we want to reduce it, so we're going to want to just divide the components of this vector by the original length. So if I take the vector 4, -2, and I multiply it by 1/2√5, then that should shrink it down so it has a length of 1. So when I simplify this, I'm going to get the vector 4/2√5, which is 2/√5, and then we can rationalize that in a minute. And then we're going to have -1/√5. And so if I rationalize that, I'm going to get 2√5/5, comma, -√5/5. Maybe we should double check and make sure that this does have a magnitude of 1. So to figure out the magnitude, I'm going to do the square root of the x component squared. When I square 2√5/5, I'm going to get 4 times 5/25. And then when I square the y component, I'm going to get 5/25. And so that's going to give me 20/25 plus 5/25, which is 25/25, which is 1, and the square root of 1 is 1. So there's your answer. All right, so let's talk a little bit more about vectors, especially these vectors that have a length of 1. We're going to call those unit vectors, kind of like the unit circle. We call it the unit circle because it has a radius of 1. So unit vectors have a magnitude of 1. So if I draw the vectors 1, 0, and 0, 1, starting at the origin. So let's say green for 1, 0. That's there. And for 0, 1, that's there. And we actually have special names for these two vectors. So the vector 1, 0 is referred to as vector I, and the vector 0, 1 is referred to as vector j. So now if I draw a vector, let's say 5, 2. So go ahead and do that in a different color. So over 5 up 2, it's right to there. What I'd like to do is to be able to represent this as a combination of the I vector and the j vector. So if I could take this I vector and if I multiplied it by 5, that would be 5 times I. And then the j vector, if I multiplied that by 2, and then if I added the 5i vector plus the 2j vector, that would give me my vector 5, 2, which is what I started with. So we've learned that we can talk about a vector with the coordinates of the initial point and the terminal point, or we can write it in component form. And now we have another form we can write it in, what I call ij form. And so we would write for this 5i plus 2j. And remember, I is the vector 1, 0. So this is the same as saying 5 times the vector 1, 0 plus 2 times the vector 0, 1. And if we perform the scalar multiplication, this becomes the vector 5, 0. And this becomes the vector 0, 2. And then when we add those together, the x components added give us 5, and the y components give us 2. And that indeed was the vector v that we were talking about. So it's just another way of writing a vector. We've got component form, and we've got the ij form, or we can write it with the 2 points with coordinates for the initial and terminal. All right, let's look at these 2 points, P and Q. First of all, write PQ, well, let's write PQ as a linear combination of the standard unit vectors I and j. So I guess the first thing I'd like to do is just write it in component form. This time I'm going to write it with the parentheses instead of the other way, just so you're familiar with both notations. So from P to Q, that's going to be 13, negative 7. So that's the component form of our vector. And so therefore, that means that it's 13i minus 7j. And that's it. Easy enough. Another example, let v be the vector 2i minus 4j, and w is the vector 5i plus j. Find 2v minus 3w. So it's probably exactly what you would think. So 2v means I'm going to do 2 times 2i minus 4j. And then I'm going to do 3 times w, which is 5i plus j. So that's going to give me 4i minus 8j minus 15i plus 3j. And distribute that subtraction sign. So we're going to have 4i minus 15i is negative 11i. And negative 8j minus 3j is negative 11j. Now since the original problem was written as a linear combination of I and j, it makes sense that my answer should be in terms of I and j. On the other hand, somebody could have looked at this and said, well, 2, negative 4, I could write this way, and 5i plus j, I could write this way. And then 2v is 2 times the green vector, so that's 4, negative 8. And 3 times w is going to be 15 and 3. So then when I do 4 minus 15, I get negative 11. And negative 8 minus 3, negative 11. And that's the same as that. Okay, let's look at another example. If u is equal to 3i plus 4j, find the magnitude of u. and then find the angle that that vector u makes with the positive x-axis. So let's find the magnitude, 3i plus 4j. Well, we know now that the component form of that is just going to be 3 comma 4. So the magnitude of vector u will be the square root of the x component squared plus y component squared. And there's a Pythagorean triple. So we know that it has a magnitude of 5. Let's draw this over on a graph. 3 and 4. There's our vector. So now the second part of the question says, what's the angle that this makes with the positive x-axis? Well, if we just use trigonometry, we'll make a right triangle here. We're trying to find this angle theta. This is 3, this is 4. That would be the opposite and the adjacent. That's tangent. So I know that the tangent of theta should equal opposite over adjacent 4/3. So going back here, there we go. Find the angle it makes. Theta, the angle it makes with the x-axis, is going to be the inverse tangent of 4/3. And then we can grab a calculator, and if I have one handy here, and let's make sure I'm in degree mode. Okay, and then we'll just do second tangent 4/3. About 53.13 degrees. And that makes sense from the picture. That looked like more than 45 degrees, but not a lot more than 45 degrees. So that angle that we just figured out, that's referred to as the direction angle. And to find the direction angle, you just do the inverse tangent of the y component over the x component. Okay, so now you should be ready to finish the rest of those problems on worksheet 1.2.